So as I've just been introduced, this is Timing and Benchmarking Scientific Python by me. I'm a software developer at BHP and a SciPy maintainer. If you want to get the slides, they're available on GitHub, and that's the URL. It's a little bit long, but it's basically just my GitHub and then EuroSciPy, and then the first PDF in there. So a quick disclaimer before I start. I'm not a statistician. So a lot of this is looking at statistics, it's looking at how I do it and how it's been useful in my life, rather than what's the proper theoretical statistical way of doing it. So what we're going to cover. There's quite a few sections, but I'll try to get through them relatively quickly. So we're going to talk about why this talk, why does time matter, we're going to talk about thinking of an experiment, and then we're going to basically build it up from there to comparing groups of benchmarks. So why this talk? This talk was supposed to be something else. Supposed to be looking at timing and benchmarking the SciPy ecosystem, analysing the methodology of different articles and papers in the scientific ecosystem, discuss what is done well and where we can make improvements, and then apply these points to SciPy's benchmarking suite. Unfortunately, that didn't happen. So a lot of papers don't look at performance in scientific Python, and of those that do, many lack adequate statistical analysis of their results, and even more of them didn't even state their methodology. So what will this talk be? This is going to be advocating for a statistically rigorous approach to timing. That means it covers topics you should consider when timing, and benchmarking as well. What this talk is not. So this is not going to be a new standard on how we construct benchmarks or how we should construct benchmarks. This is just going to be going over what I find useful and what I think you should know as well. So firstly, why does time even matter? I mean, we're all here to talk about it, so it must matter to some people. But why? So there's a common problem. Say you're at work. You have two solutions, S and S prime. You're told that S runs in 100 seconds and S prime runs in 95 seconds. Which one's faster? That's not a very hard question. I think everyone's going to say the 95 seconds unless you're some kind of joker. But how sure are you that it's faster? So your co-worker's just come up to you and said, I've got these two timings. How much do you know about it? You don't know. They could have been on different machines. They could have been comparing different programs. You want to be sure that this is actually what it states on the box. So the problem here is that computers can reproduce answers, not performance. So here I've got a time it run, where we just take the sum of squares for a very, very large number, and we see it runs in 343 milliseconds. Run it again, takes 310 milliseconds. Run it again, takes 312 milliseconds. So which one of these runs is the true time? And the answer is we can't tell you that. We don't know. So this variance makes timing measurement hard. So computers can reproduce answers bit for bit. They cannot reproduce time. And time is also important. So who here likes waiting? I'm going to say that's basically no one. And there are also many performance metrics, many of which depend on time. So accurate timing measurement is crucial for those reporting metrics. But we usually don't measure time well. The rigorous benchmarking performance analysis methodologies are lacking in Python. Different studies use different and often ad hoc methodologies, and even different tools will use different methodologies to make their timing. And many lack a truly statistical treatment of their results. And again, many didn't even state their methodology, which is hard to compare it when you don't know what they've done. They've just given you a number. So what I said before about statistically rigorous, I think there are three kinds of lies. Lies, damned lies, and statistics. This is going to teach you how to ideally not lie with statistics. So what am I proposing here? I'm proposing that we think of timing as an experiment. So what makes a good experiment? There's a clear hypothesis, so we know what we're testing, we know what we're looking at, we know what we're comparing. It's relevant, so we're timing something that's actually relevant to our statement. It's replicable, so if we run it again, we'll get a similar time. We might not get exactly the same time because computers can't reproduce answers, but we will get a similar kind of measurement. And it's documented. So all stages of the experiment, or in this case our timing run, are documented so that other people can reproduce it, so that we can reproduce it in 6 months. So what do we measure? Firstly, there's clock cycles. These aren't that relevant in Python because Python has a lot of overhead. It's an interpreted language. What I propose we measure more is time. So just wall clock time or CPU time. So how do we make the benchmarks reproducible? My principle is that benchmarks should require as little human effort as possible to understand and to be run. There are two main tools to doing this: documentation and automation. So firstly, let's talk about documentation. There are a couple of points here. So firstly, clarity. So documentation helps make it more clear what you're doing, why you're doing it, how you're doing it. It makes it reproducible. So if people know what you're doing, they can reproduce it. They can test it on their machine to see how it compares. Maintenance. So over time, software undergoes changes, and maintaining up-to-date documentation helps to modify the benchmarking suite without confusion. And again, it means other maintainers can come on and reproduce your results. There's also automation. So firstly, it makes it consistent. It makes it scalable. So as the benchmarking suite grows, you can grow it more and more easily, and you don't need to manually run all your benchmarks every time you want to test something, because that becomes very, very difficult. And there's continuous integration. So this way you can run your benchmarks every time there's a pull request if you really wanted to. I don't recommend doing that because it becomes very resource intensive, but maybe if you run it once a week automatically, see if there are any performance regressions, I think that's a very good idea to begin with. So how do we take a single measurement? Taking a single measurement is important because you can't fix by analysis what you bungled by design. Basically, if you start taking measurements wrong, you're going to be analysing the wrong data, which is going to lead to garbage out. So garbage in, garbage out, basically. So what affects a single measurement? And there's a lot of this, which I'm not going to cover in too much depth because I could talk about it basically all day. So there's the observer effect and there's hardware effects. So what's the observer effect? All forms of instrumentation change the result. So basically, running a profiler, running a timing suite, running a benchmarking suite changes the result. Instrumentation normally adds overhead. Basically, if you're running your suite plus something to measure the time, it's going to use more resources than if you just run the thing. And there's this quote that I really like, which was that you thought that the code was slow to start with, so you made it slower to see how slow it was, which is true. So you need to keep that in mind when analysing your benchmarks. It will be slightly slower than if you just run it manually. What about hardware effects? There are many, many, many possible effects. So Microwitz showed that, for example, link order and environment variable size can significantly affect your measurement. I think in that original paper they showed that it could change performance by about 40% of a simple C program, which is very significant. And this is mainly noticeable in low-level languages. So why do we care in Python? Well, Python is basically C, Rust, C++, Fortran code. Especially in the scientific world, it's basically low-level languages wrapped in Python. It's glue. What about garbage collection? So CPython implements a stop the world garbage collector. So that means that the garbage collection can freeze your program at any point. I think it's important to account for that as you're running your benchmarks. So the GC module provides an interface to the garbage collector, which you can use to control the garbage collector. And I'd consider performing the garbage collection, then disabling the garbage collector before taking a measurement. So that's basically how you do it in Python. So that means that as you run your measurement, you're not going to have the garbage collector appear in the middle of it and start to interfere with your results. What about warm-ups and steady state? So the first values of each worker run are normally slower. Overhead can vary quite a bit, especially when you're using a JIT compiler like PyPI or Number. That's because it does a compilation step to begin with. But that is still present even in C, Python, and other non-JIT compiled Python implementations. And many benchmarking suites ignore the first n values of each run to accommodate for this. So if your first run is a JIT compilation step, it's going to be much slower, so it's not going to give you an accurate benchmark. So we ignore it. And this is still a work in progress. So we don't know exactly how these work. We just know that it will be slower. We can't predict this is going to be 10 times slower or 0.5 times slower or whatever. So what about running a single benchmark? So what is a benchmark? A benchmark is a standardized test to evaluate and measure the performance of hardware, software, or a combination of both. I hope everyone knows that by coming to this talk already. And they're useful for performance analysis. So basically, computers are very, very complicated machines. We can't really predict in practice how fast it's going to run just by looking at the specs or just by analyzing a program analytically. And this may not always reflect real-world usage scenarios accurately, so it's important that your benchmarks reflect what you're doing in the real world. So what's out there? I'm not going to write a benchmarking suite from scratch because it already exists. I hope you don't write a benchmarking suite from scratch because there's some that already exist. If you do write one, I'd like to see it because I'm interested in this, but yeah. So basically just time it. So this is an inbuilt Python module to measure the execution time of small code snippets. It performs multiple runs of the statement and returns the average of the minimum time of each run. So it might do 7 runs, find the minimum of each run, and then take the average of that minimum. There's PyPerf. So it's a toolkit to write, run, and analyze benchmarks. It's useful because it can automatically calibrate a benchmark for a time budget. So if you have an hour to run your benchmarks, it'll try and get the most accurate result within an hour. And it can detect if a benchmark seems unstable. There's also airspeed velocity. So that's a tool for benchmarking packages over their lifetime. So that'll go by commit, run the benchmark, and show you the results. It returns runtime, memory consumption, custom-made events, whatever you want. So you can just return a method or a function which will return a result and run it for you. And it's used by many free and open source projects like AstroPy, NumPy, and SciPy, or the basis of many of theirs. And there's the link if you want to have a look at it. So how do we design a benchmark? Well, firstly, we need to figure out what we're actually going to look at. So for example, we talked before how time it takes the minimum, the average of the minimums, but that seems quite counterintuitive to me. So why do we take that? Well, the minimum time is basically a frictionless model of your result. So it shows you how fast it could run in the best case scenario. The average time is different because it means that due to the law of large numbers, your results become more accurate over time. This is what's used by PyPerformance or PyPerf, which in my opinion is the better metric. Also, if you're taking the average, which average do you use? So for example, PyPy cites the geometric mean as their average, which is controversial because if you take the arithmetic mean, it gives a different result and it becomes less comparable. So next, can we assume a normal distribution? So normality is assumed in many, many, many benchmarking suites. The distribution of results might not always follow a normal distribution, and in this case we need to adopt different statistical tools. So we can still look at it statistically, we just need to, if it's not normal, treat it differently. So how do we test for a normal distribution? So basically it's important to look at it. First one's just visually eyeballing it. So I'm sure everyone knows what a normal distribution looks like. It's that bell curve. If it's obviously skewed or obviously bimodal or something, then you can tell it's not normal. You can visualize it with a QQ plot. So there you're looking for the tails to be out of alignment. Or there are many statistical tests which can be employed to formally assess the normality assumption. This can get a bit tricky because normally you won't be taking a very large number of measurements. So you need to take a test that's robust to having small measurements. There's one more simple error check that I use. So I like to look at the minimum and the average, so both of the measurements we talked about before, and then look at the distance between them. So if the minimum is much lower than the average, or much higher than, it can't be higher than the average, but much lower than the average, then it's probably not normal because outliers are rare in normal distributions. And this was brought up by Lemire at a 2023 talk, which I actually really recommend you watch as well. So there's some more error checks. This is for an unstable benchmark rather than for normality, but the standard deviation is greater than 10% of the mean. So I've found that, as a rule of thumb, if the standard deviation is really high, it's not going to be reliable. The minimum or the maximum is 50% smaller or greater than the mean. Again, this is showing that there's some kind of noise being introduced, so it's hard to analyze it statistically. And the shortest raw value takes less than 1 millisecond. So our tools in Python aren't that precise, so we want to make sure that we've got at least a millisecond of runtime. What about outliers? So you need to look at them carefully. It's important to understand how it affects the benchmark. So it's quite rare for it to reduce runtime, but it might. And it's important to understand, so did it only affect some values? Did it affect all runs? And so some performance libraries, like High Performance, actually choose to include outliers because it's more realistic of what's happening to their data. And these may or may not be included in your analysis. So that's a design decision that you should make, document, and yeah. What about our benchmark? So I'm going to look at the Pi Performance benchmark. This is an authoritative source of benchmarks for all Python implementations. So this compares benchmarks like CPython, PyPy, Python, all those kind of ones to see how well they perform compared to each other. The focus is on real-world benchmarks, so we don't have many micro benchmarks, and it includes the ability to add your own benchmarks if you choose to modify it. And there's the GitHub link for people who are interested. So this is an official Python project as well to keep up with the different implementations. What I'm going to be looking at is one benchmark specifically for now, which is the n-body benchmark. So the n-body benchmark is from the computer language benchmarks game. It models the orbits of Jovian planets using a simple integrator. And there doesn't exist an analytical solution if n is greater than 2, so if there's more than 2 bodies. And this is a micro benchmark on floating point operations. So firstly, eyeballing the distribution. To me, that doesn't look that normal because you've got 2 lumps, which is not what you expect to see in a normal distribution. We are still using very small numbers, so we need to be a bit careful about our normality assumption, but just intuitively it doesn't look normal, so I'm going to be very skeptical of most of the standard benchmarks. There's the summary statistics, so we can see we've got 20 samples, 20 runs, we've got the mean, standard deviation, all that stuff for you to look at. So what about our simple error checks? The minimum time of the run is 48 milliseconds, sorry. The mean is 48.7 milliseconds, so they're very close together. So that's a good sign. Let's look at our stability checks. The standard deviation is 1% of the mean. That's much less than the 10% we allowed ourselves. The minimum and maximum are very close together, which is good. Very close to the mean. And the shortest raw value took 48 milliseconds, which is much longer than 1 millisecond. So how do we compare this to something else? So does Windows or Linux run faster? So we want to compare how a change in the OS affects our runtime performance. I ran the benchmarks on Linux and Windows. It was dual booted on my PC, so all the hardware was the same, and I was careful to make it as unbiased as I could. So they were both in high performance mode, they both had no background tasks running, all that kind of stuff. So let's look at the statistics. Linux ran with a mean time of 49 milliseconds. Windows ran with a mean time of 70 milliseconds, which I think is quite significant. So in this case, it's obvious. We've got a distribution of, we've got the two distributions, there's no overlap. It's pretty obvious that Linux ran faster. But what about this benchmark? So this is the SymPy-Sum benchmark from the same benchmarking suite. Is it easy to say that one is significantly faster than the other? I don't think so, at least not just by eyeballing it. So the trick here is to compare distributions, not summaries. This doesn't increase the sample size. This lets you look at the sample size. This lets you look at the quality of your data. It's generally going to be quite low because you've got a low number of runs. The distributions capture the variability in the data. There's skewness and asymmetry relatively often, just because of the small sample size. So what about comparing groups of benchmarks? What are we trying to do here? We're trying to answer a question. How does our change affect the system? A single benchmark doesn't tell us much about the system as a whole. It only shows us about one facet of the system. We want to understand how the system as a whole changes, and need to compare multiple relevant benchmarks for each part of the system. So back to the Pi performance benchmark. There are a total of 95 benchmarks. On some of them, Linux is faster, on some Windows is faster. So for example, on the left, Linux is much faster than Windows. On the right, or B, Linux is much slower than Windows. So here's a simple test to see which is faster. So I just count the number of times Linux appears as significantly faster, compare how likely this is due to chance, and if significant, consider one with a higher count as faster. So is Linux and Windows faster? Linux is faster 78 times, Windows is faster 15 times, and the difference is statistically insignificant twice. And so according to our rule of thumb, Linux is faster. So in conclusion, what you should take away from this talk: timing is hard because of variance in your measurements. Different methods, each with their own trade-offs, exist, so make sure your choices are relevant to your real work. Document and automate your benchmarks so that they can be run by others and that they can be run reproducibly. And analyze distributions, not summary statistics. And let's stay in touch. Thank you.
Thank you very much, Kai, for this very interesting talk. I guess there are some questions. Just raise your hand and pass the microphone.
So what you mentioned, you run the model multiple times and then you get this distribution really of with the variance as well. But for some models, some large machine learning models maybe, like one run can take already a long time. So do you have some solutions for if you're not able to run it really like 10 times?
So I would just run it with a smaller input size and see if that still works. But yeah, it becomes very hard to do it statistically if you have very large models. So I don't have a good solution to it, but I have a suggestion, but that's about it.
So with a tool like ASV, you get performance metrics over time, but not individual runs in a distribution from that. But I can take the performance metrics over time from various runs of ASV and then look at that as being a distribution. Does analyzing that change how, or does the origin of this data kind of change how you would analyze the distribution versus lots of runs for one particular benchmark? Does the question make sense?
It makes sense. I'm just trying to think about it for a second. So what you're saying is you're drawing distributions over time, a distribution from time, rather than a single run in one period of time.
Right, because ASV only gives me a time for each benchmark run, and I get that for various commits, but I don't get a whole distribution for each commit.
I wouldn't try that just because your code's changing over time as well. So what ASV is really good for is looking at regressions in your performance and not at the individual runs. I'd prefer it if ASV gave you back the distribution. I think that'd be really good, but they don't do that yet.
Excellent, excellent, thanks. And yeah, not only is our code changing, but dependencies too, and that creates a whole bunch of noise.
Yeah.
Further questions? We still have time.
Thanks for the talk. That was very interesting. Could you tell us a few hardware-related horror stories? You said there was many. I always think of thermal effects first, but what are the worst?
So, for example, one, going back to that paper, is the environment variable size, which changes where your memory is allocated in the program, I think. I'm not much of a hardware person, so it's a bit, I'm a software person, not a hardware person, but that can introduce changes of about 40%, according to them, according to that paper, which is significant, to say the least. I think there's a similar change where they had dead code. So this is actually from Victor Stinner's blog, who's a C Python core developer, and he found a slowdown of about 17% due to a similar thing, where they had dead code. They weren't using the profile guided optimization, so it was included somewhere. And that changed it by 17% for one commit where they didn't change the code. So that was very hard to debug.
So do you have advice if the data is not normally distributed to investigate and find why it's not normal distribution?
Yeah, so firstly, it might just be because it's a small sample size. So it depends how much you've taken. So the first thing would just be to get more samples if that's feasible. We had the point before that some processes take a very long time, so that's not feasible. The second point would be to look at how your computer's interacting. So like, is it getting it from memory? Is it getting it from the CPU state? So that's what I would look at. That's where, in my experience, most of the slowdown comes from. But yeah, it's a hard question. So it's, yeah.
Okay, we have time for one more question. So if somebody wants to ask a question during the talk, please raise your hand. Doesn't seem to be the case. So thanks again, Kai, for this great talk.